Alrighty guys, this is the second half of the online video lesson. So in this video, we'll be looking at normal approximations to the binomial. But before that, we'll be recapping the 2-unit content, which is the normal distributions with z-scores and the z-score tables, etc. I'm not sure if you guys have learned this at school at this point in time. So we'll do a quick recap and hopefully you guys have covered it to some extent because we'll be going through it fairly quickly. Now, the normal distribution is an example of a continuous probability distribution. And it's just kind of explaining how the probability is spread out across different continuous outcomes. And I'll explain that a little bit more as we get to the diagrams. But the normal distribution isn't the only example of a continuous distribution. There's some other ones, including the log normal, the gamma distribution. As I was mentioning in the previous video, if you go on to do actuarial, you'll look at these other distributions. They have different shapes. Essentially, they distribute their probability in a different way across the outcomes. They're skewed one way or the other. Normal distributions are centered around the mean. Okay, so let's have a look at some of the notation. So if we have a random variable, let's say it's x, we can say that that variable is a variable that's distributed as a normal distribution if we write it in this way. So what it's saying is this random variable has a mean mu and variance sigma squared. And you would have seen, or maybe you haven't yet, but the z-score is calculated by looking at our outcome minus the average divided by the standard deviation. Or in other words, what this is saying is how far is my outcome, or how many standard deviations is my outcome from the mean. So this is an interesting concept because let's say that we have a class average of 50 in English, and then we have a class average of 60 in maths. And let's say that someone scores, 70 in English and then 70 in maths. And maybe you remember this from year 10, but it's a question of which subject did they actually perform relatively better in. This is 20 points above the average, while this is 10. But it could be that they actually relatively perform better in maths if the exam was, say, more difficult and more students scored around the mean. So, most students actually got, say, 55 to 65. So getting 70 is actually more of an outlier. Whereas in English, this could have a lot more volatility. Like the average could be 50, but you could have a lot of, low scores, 10, say 15, and then a lot of high scores as well that results in an average of 50. So overall, if you get 70, you haven't actually performed that much better than the rest of the class. So this is where this idea of z-score comes in. We look at it in terms of how far am I away from the mean or the average, and this is actually connected back to probability, because to be more standard deviations away from the average means that it's harder to get that score, or you're less likely to get that score. That's why it's an outlier. In what's like kind of intrinsically, or what's not being said here, is that it's a less probability to have an outlier or have a score that's further away from the average, and we'll get to that in a bit. Now, we can actually describe the shape of the curve. So if you think about the bell curve, the normal distribution, it looks something like this. And because this is a curve, it has an equation, has this very complicated looking equation. We won't be doing anything with this equation, but again, if you're going to do actuarial, you will be playing around with this equation. But let's skip right to this page here, which is we're looking at some specific values or specific probabilities, critical values. And these values we'll be using often in our questions. So when we look at the area under a normal distribution curve, or under any probability distribution curve, or function, it should add up to 1. The area should add up to 1, because what these curves are describing is how is my probability of 1 spread out over my outcomes. And what you'll notice is that it's centered around the average, and that makes sense because in nature, when you have a normal distribution, it's usually down to some randomness. It could be like if you map out heights of people, most people would be around the average. And then as you get further away from the average, it's less likely that you'll have, people at those, say, heights. So for example, if my average height is 160, you might have some people sitting at 180, but then as you get further away at say 200 centimeters and then 220, it gets more and more unlikely that you would have those people at those heights. Okay, now the other thing is because these are continuous outcomes, to get the probability of any one outcome is basically 0. That's because if we're saying, okay, we want someone with a height of 160, what that really means is that I'm looking for someone with a height of 160.000, all the way, like all the decimal places needs to be 0. Like we're looking for someone who's exactly 160 centimeters. What happens if someone is 160.01? Like that could be their height, so they don't fall into this. So that's why when we look at continuous variables, we actually need to look at a range of values because otherwise our probability is 0. So we go, okay, what's the probability that we have heights from 150 to 170? And then we'll look at it in that way and we'll find the probability that way. Now, we look at specific values because we have known probabilities for them. And that's where the z-score table comes in. Because the equation is quite complicated, it's hard to find the area under these curves. So that's why we look at either standardized values like this, so these percentages are easy to remember, or we have the z-score table that gives us more granular standard deviations. We could be looking at, like 1.1 standard deviations away, for example, from the mean, and we have a value for that in the z-score tables. So we'll get to that a little bit later. Okay, so if we're looking at this example here, this is saying, okay, we are 1 standard deviation above and below the mean. So if we were to look at that area, that would give us 68%. So there's a 68% chance that you'll be within 1 standard deviation, up or down, of the average. When we look at 2 standard deviations, this is a bigger area. We're covering more outcomes, and that's 95%. And when looking at 3 standard deviations, this is 99.7% of all probability falls within, or the chance of getting something between 3 standard deviations is 99.7. Now, the other thing to note here is the probability in the tails, because this is something that will come into use in the questions. So if we have a look at the 95% one, for example, there's a total of 5% in the tails. And because the normal distribution is symmetric, there would be 2.5% in each of the tails. All right, and in this case, we are missing 32%, so that would be spread out over the 2 tails. And so we would have 16% here, and then here we would just have 0.15% in each of the tails. Okay, hopefully that makes sense. Okay, and now the next concept. So it's a little bit hard to work with, numbers. Like for example, in this case, we could be looking at, I don't know, like the number of people in a school, the number of students in a school. So we've got 1,010 as the average, and then so on and so forth. When looking at these, it's a little tricky to work with probability. So what we do is we like to standardize it. And all this does is it just centers it and makes the standard deviation 1. And that just makes it very easy to refer back to these standardized probabilities. That's why we always look at z-score. And when we look at a standard normal distribution, and if it's not a standard normal distribution, we look at it in terms of z-score, which is effectively bringing any normal distribution into a standardized normal distribution. The way that we do that is just by using this formula. We just effectively subtract the average from all of our outcomes, and then we divide it by the standard deviation. So that would take us from something like this to the one that we see on the right. And the normal distribution the standardized normal distribution has this format. It's now got a mean of 0 and a variance of 1, which is exactly what we're looking for. It's centered over the average, and each standard deviation is equal to 1. Whereas in this case, the standard deviations are equal to 20, and it's standardized over 1010. The probabilities that both of these will capture will be exactly the same. So it just makes it easier for us to work with. Okay, here's the next concept. We're looking at the symmetry of the normal distribution. And I mentioned this earlier. The reason why we're looking at this is because a lot of the time, the z-score tables will only tell us a probability of having a value or less. So for example, the z-score here could be 1, and our z-score table, the table itself, gives this particular probability here. Now, what happens if we're looking for a probability where we need to look at above a certain value? So for example, this could be specified as 10%. P Z is less than -1 could be 10%, but we need to figure out what is the probability that we have more than 1. Well, in this case, because it's symmetric, this area here and this area here are the same. So this would also be equal to 10%. And what I recommend is that you guys always draw a sketch of the probability that you're trying to find, and that'll make it easy to work with the z-score tables. Another example is we might be looking at a probability between some values. So for example, A and B. If we're looking for that probability, keeping in mind that the z-score table usually only has probabilities of less than a value, we would look at, say, this value here, less than B, and then less than A. And then if we subtract these two, so let's say that we subtract this will leave us with this area that we're interested in. So that's just how you would go about using the z-score tables to calculate particular ranges of values. Okay, and we saw this earlier. This is just a summary. When we're between 1 standard deviation, we have this much probability. Between 2, we have this much. Between 3, we have this much. Okay, I'm going to take you guys through this question very quickly so that you guys at least have a sense of how to use these z-scores. We don't have any examples this time around, so we'll either try this question again if we have time in class. Just let your tutor know that you've already covered this question. Otherwise, if you have time, have a go at it again. So let's read through the question. A number of fish species are subject to minimum length regulations when they are caught. So by the way, this question comes from one of the Holston trial papers. I.e., fish shorter than a given length must be returned to the water if caught. Two such species are the red snapper and barramundi, which have minimum lengths of 30 and 55 centimeters respectively. So let me just write this down because this question is quite wordy. So the minimum lengths for the red snapper is equal to 30, and for the barramundi, maybe I'll just write it with B, the barramundi is 55. A fishing tour operator in North Australia has made observations over a long period of time and found that when measured in centimeters, both the variables are the length of the red snapper and B are normally distributed. R has a mean. Okay, let's use our notation. Has a mean of 36 and a standard deviation of 9. So if we write it using our notation, remember it's a variance. And for the barramundi, this is also normally distributed. We don't know the average, so we'll just say it's mu, but we know the standard deviation, so the variance is 16. Okay, part A. Calculate the mean length of the barramundi caught if 2.5% of barramundi are less than 54 centimeters. Okay, so this is, at first glance, a very confusing question, but let's put this on a diagram. So we know that, and this is a terrible normal graph, but we know that the barramundi are distributed normally. And we're saying that at a length of 54, so let's say that this is 54, less than 2.5% are length of 54. So if we're looking at 54 centimeters or less, the probability of that is 2.5%. Now, if we go back to these graphs here, this tail probability corresponds with this middle graph here. So to have a probability of 2.5% in the tail, we need to be 2 standard deviations to the left of the average. So if we come back to this the distance between this value here, 54, and the mean is 2 standard deviations. So to get to the mean, we will just get our value of 54 and add 2 standard deviations. And the standard deviations for the barramundi is 4. And so we have 54 plus 8, which would be 62 centimeters. So now we can complete our barramundi normal distribution and see if that comes in handy later on. All right, part B. Calculate the z-scores for the minimum allowed lengths for both variables R and B and comment upon what this means in terms of which species are more likely to be returned to the water after capture. So just on this part, for it to be less likely to be returned to the water after capture would mean that we have a higher, more likely would mean that we have a lower z-score. Sorry, I'm having a bit of a... Yeah, let's actually come back to this one. I think in context it will make a bit more sense. But yeah, let's keep an eye on this. So if it's more likely to be returned to the water, it means that we need to be closer to our average, because being closer to average would mean that there's more of a chance of that happening. And so if the minimum length is closer to the average, i.e. a smaller absolute value or smaller magnitude of the standard deviation, that means it has a higher chance. But let's work it out and make a bit more sense. So the z-score of the red snapper, and what this is asking really is what, these minimum lengths, how many standard deviations are they away from the average? So for the red snapper, it's 30, and I'm essentially 6 units away, but I want to get that in terms of standard deviations. My standard deviation, remember, is 3, and this is 2 standard deviations away. For the barramundi, my minimum length is 55, and it's 62, and my standard deviation is 4. This would be 1.75. So this here is like less far away from the average than this 30. Although this is 6 units away and this is 7 units away, the barramundi is less standard deviations away. And so because it's closer to the mean, the chances of getting a fish with a minimum length is higher than it is when compared to the red snapper. And so the barramundi, actually, I won't write it out, but the barramundi has a higher chance of being returned. Okay, there's some additional practice questions here for you guys that you can try if there's time, but I might get you guys to skip that if we're short on time. And I will very quickly talk us through this theory here, and then we'll try these 2 examples. Okay, now in the last video, we saw that when we have a lot of outcomes, the binomial distribution starts to become, similar to a normal distribution. So if we have, for example, this distribution where we have n outcomes and we have a probability of half. And here's the thing, like the probability, if it's half, that's when you'll more typically be a normal distribution. Because if you imagine, if it's something like, for example, the probability of a success is 0.1, it would be like really skewed towards the left, and that wouldn't be a normal distribution. That would be a different kind of distribution. And likewise, if we have it here, it wouldn't really be a normal distribution either. But I suppose if we have enough iterations, then we may be able to approximate that, and we'll get into that a little bit later. Okay, so if we have this binomial distribution, we can approximate it as this normal distribution, and we'll get into that a little bit later. But you can see if I had bars here at each of these outcomes, here they've just represented as dots. You can see it starts to take on the normal distribution form. And here this point is saying that if n is small, then we'll need a correction when we're moving from binomial to a normal, because it doesn't, you can see that there's some missing spaces. That's kind of outside the scope of this course. In fact, this content won't really come up. Like what we'll get more of is the binomial probability stuff. So I should have mentioned that at the beginning of the lesson. But this content is kind of like the brine, the concentration type of questions that we looked at, where we're learning it just in case it comes up. Okay, so let's have a look at this content, this theory really quickly. For a fixed number of n trials, the normal approximation becomes less accurate because it's more skewed, and the distribution, the more skewed the distribution becomes, which makes sense because you have less bars, and they're more prone to being skewed one way or the other. For a fixed probability P, the normal approximation increases in accuracy as the number of trials increase. So like I was saying before, if it's skewed, let's say, I have all my bars on this side and it's skewed, it won't be the best approximation, but we can still use a normal distribution to approximate the probability. And the way that we know whether it's going to be like decently accurate or not is by looking at this rule of thumb here. So if we multiply our number of outcomes with the probability of success and it's more than 5, and same with the probability of failure, it's more than 5, this will have a decent distribution to approximate using a normal. And that kind of makes sense because we don't want this to be like skewed one or the other. Like we could get 5 pretty easy by going 10 with a probability of 0.9. This is like equal to 9, which is more than 5. But then on this side, it doesn't meet that criteria. So if we do want a heavily skewed probability, we need many trials to make sure that we have it more than 5. Okay, one thing that isn't quite spelled out here is when we're going to the normal distribution, the mu here is coming, and the standard deviation here from the binomial is coming from the formulas that we looked at before. So for the mean, the average is the number of successes times the probability of success, and the variance is going to be n times p times q. So in this case, it's going to be 20 times half, which gives us 5. So let's keep these in mind as we do the first example, and I'm kind of running out of time today, so I'm going to just take us through the first example. A coin is tossed 20 times, so this is our n, and x is the number of heads. Find the probability that the number of heads is greater than 12 using a binomial distribution. Do not evaluate. So here's the thing, when we have a lot of trials, it becomes difficult to calculate the binomial probability, because have a look at what we need to do. We need to do 20, all right, see 12, and then the probability of success is 0.5, and we got to go 12 and then 12, and then we would need to look at 13, and then we would need to look at sorry, not 12, this would be 8, and then this would be 7, this would be 13, and then we have 20, then 14, and then we have this, and then so on. So there would be many that we need to evaluate. But when it comes to normal distribution, if we can approximate it using a normal distribution, so what we can say instead is we have our, let's say random variable x. I'm going to approximate this as a normal. So my average is going to be the number of number of trials times the probability of success. So that's going to be 10, and then my variance is going to be 20 times 0.5 times 0.5, so exactly the same as the example that we just saw. Okay, so what we are looking for in this case is a probability that it's more than 12. Now, here's where the continuity correction comes in, and this is a little bit confusing, and I don't know to what extent this will be taught at school, and I'm suspecting these questions won't really come up, but we have an average of 10 here, and we're looking for more than 12. And the thing is, we don't really have, if we're looking at more than 12, normally because it's whole numbers, we would be looking at 13 or more. In fact, I shouldn't have included the 12 outcome here, so let me get rid of that. So we would be looking at 13 or more. And in this case, because we technically need to jump up to 13, but since this is now being approximated as a continuous distribution, was essentially skipping from 12 to 13, and we're missing out on all of this stuff in between. So to approximate that loss, we're going to essentially start from 12.5, and we'll go into more on this in class. There's a example that will describe which continuity correction to use in which circumstance, but because I'm a little bit low on time here, we need to approximate it from 12.5. Now, this is a non-standardized normal distribution, so we can't use a z-score table. So what I would do is I'll convert, instead of outcomes, I'll convert into a z-score. So I need to see what 12.5 is as a z-score, or how far it is from the mean in terms of standard deviation. So I have 12.5, my score, minus the average, and I'm going to divide this by root 5. And actually this should have an equality, but it doesn't matter really, since it's doesn't really matter since it's a continuous distribution. And so if I evaluate this stuff on the right hand side, I get z is greater than or equal to 1.11. And what I need to look for in the z-score table, depending on how it's set up, and most of the time it's less than a certain value. So if I find 1.118 or 1.2, depending on how many decimal places I have in my z-score table, the value that is going to be giving me is less than that point, but I need the value that's above that point. So in the z-score table that we will be getting, it will be less than that, and the z-score that we would get is 0.8686, and this will come out to 0.1314. So the probability of getting more than 12 heads is approximately 0.1314. And the reason why the binomial, a normal approximation to the binomial is so handy is because rather than having to evaluate all of these, we can approximate it using the normal distribution. We can calculate the probability from that distribution, and we get 0.1314. That's it for this video. Let me know if you guys have any questions, and